All right, chapter 6.2 deals with line integrals. And what a line integral can do, they let us integrate multivariable functions in vector fields over curves on a plane or even in space. So you're going to have some sort of either two-dimensional or three-dimensional parts, so either two variables or three variables, and you're going to need to make some sort of parameterization with this. And our new parameter is just going to be t. You're going to write everything with respect to t. So we'll have this RT here be our new value. So again, with a lot of the things for integration, our function has to be continuous. And the domain has to include some sort of smooth curve, C. And again, the smooth curve could be just a line. That's not an issue, but essentially no sharp points like you would find at like an absolute value or something like that. All right, so the formula here, we have our integral with respect to the curve C. You can see the C down here. And we have to reparameterize it to be t, and when we're integrating it, we have the values that t can be, again, from a to b. So we figure out where our t can be once we do find the new parameter. And then we're going to take the function of whatever that vector is, r of t, and then we're going to do it by multiply that by, this is the magnitude. Let me do this in yellow. We have the double vertical lines indicating the magnitude of the derivative, and that magnitude will look something like this. Either this for three variables or this next one for two variables. Again, that's the formula for the magnitude. You take each part of the vector, the x part, the y part, and the z part if you have three. You find those values, take those derivatives, you square those derivatives, and add them up and take the square root. That's how we find the magnitude. All right, so let's see if we can just do one of these problems. So problem number 48, we want to evaluate this integral here. The C that we're looking at, so this is going to be relation to C. The C that we're looking at is a line segment, so this is just going to be an equation for a line using these two guys here. So this is, think of this as x1, y1, and this is x2, y2. So you're going to need to find the equation for the line, which again, a basic algebra class should get you through how to do that, but let's do it right now. First, you find the slope, m, and that's of course y2 minus y1 over x2 minus x1. So we have 2 minus a negative 1 in my y components, and then 1 minus a negative 2 for x. And what do I have? 3 over 3, which is just 1. And then we take one of those 2 points and determine what the actual equation for the line is. So y minus, I'll use the second point there. So y minus 2 equals 1, which is our m, and then it's x minus 1. This is point slope form, and this should get us to y equals x plus 1. All right, so now we need to figure out what the parameter t is going to be. So I'm going to suggest we're going to let t equal x. And if I plug in that x, that t and x there, that means y equals t plus 1. So we've got those values. And because our t is going to equal x, our value is t. Let's do this. So for t, the x values go from -2 to +1. So -2 will be our lowest value for t, and +1 will be our largest value for t. So we should have a pretty good setup as how this is going to work now. And we'll just need this one. So our integral our a will be -2, our b will be 1, and now we'll have to figure out what the rest of it's going to be. So we're given in this problem that our function is 4x cubed. So that should be the first part. And then we need this other part here. So the magnitude of the values here with respect to t. So this is going to be the square roots of x prime of t. Quantity squared plus y prime with respect to t, quantity squared. And then all of this will be dt. So now we can probably lose our function up there and scroll down a bit. All right, so it's cubed. All right, so let's figure out what we have here. So x prime of t, well, if x equals t, that means this is going to equal just 1. And y prime of t, well, y is equal to t plus 1. Derivative of 1 is 0, so derivative of t is 1. This also equals 1. So this is going to be the square root of 1 squared plus 1 squared. And that's where that's coming from. And that's coming from these two values there. All right. Let's rewrite this. This is root 2. So for root 2 times x cubed, excuse me. X is t, however, so we should probably just change that. We should have changed it originally, but let's change it. So t cubed dt, and let's also change this and this. So this will be t cubed, and this will be t cubed. All right, so now we just need to integrate, and the integral of t cubed, again, this we can bring the 4 root 2 out. The integral of t cubed using the basic power formula is going to be t to the 4th over 4. All that's evaluated from -2 to 1. Now, we've got a 4 in the denominator and a 4 outside, which can cancel. So this equals root 2, and then we're going to take t to the 4th power, -2 to 1. Our 1 is on top, it goes first. So that's 1 to the 4th power minus -2 to the 4th power. So we have 1, and that subtracts, was it 16? 2, 4, 8, 16. So minus 16. So that's -15 root 2, and that's how we would do that problem.